With the best of respect to our next presenter, Paul Beetham, the next presentation is a bit perverse. For all of today, we've been hearing about how we need to show off the potential for concrete. BrickPave has been doing research with Notts-Trent University showing how there is no potential. Paul, over to you.
Well, thank you, Steve, for the mysterious introduction. So,
mean that you're perverse, just subject.
Thank you. So, what we're going to go over is, in this presentation, it's a project that we developed last year with the Soil Stabilisation Task Group. So, we'll go over the need for the research, why we're looking into leaching in stabilised soil, a bit of the literature on leaching in soils in general, and then we'll look at our interim results. It's ongoing stuff, so it's a bit of like fast and loose in some ways, but I'll try and make it sound professional. For those of you that don't know what soil stabilisation is, probably most of you do, but what we're talking about is an extension of a normal earthworks operation wherein we will use a large machine like this machine here to rotate around binder around our soils. That would be either lime or cement traditionally, and that will cause improvement of the engineering properties of the material. So why do we do this? Well, fundamentally, it enables reuse of materials on site that otherwise might not be usable, and that helps reduce or limit the need to import quarried stone and avoiding landfill. So because we're mixing things like lime, this is a strong base, and so it has a pH nominally of between 12.4 and 12.5 at room temperature. So you could say there's a potential for a high pH to leach from that material into a watercourse or some groundwater. So we'll say there's potential, but if you then think of what is known and what is said about this in terms of industry literature and in our British standards, the Earthworks British Standard, which is sort of quoted here, the possibility of the binder leachate is unlikely as currently known because it should form a cemented material within the body and not move too far out of it. And there's this little quote at the end that says the migration should be negligible, less than 50 millimetres. So that's what he said about it. And it's likely in certain ways because of some of the chemistry behind this. So the solubility of calcium hydroxide, which is what the cement and the lime will have within it, is very low. And so if we were to think about that in terms of an amount, we would get about 1.6 grams per litre. That's not very many grains of salt, grains of sugar, if you think of it in that way. So that's its maximum solubility before you can't actually get any more out. So therefore, if you've got a small amount of static water, well, okay, that's going to saturate relatively rapidly, so it's not going to lead to a large scale an ongoing leaching problem. Also, a reaction that we're promoting here, so in lime is reacting with clay, we tend to form cementitious bonds like calcium silicate hydrates, and also that's what the cement itself would go to produce. And when that reacts with carbon dioxide or carbonate from air in water, we're likely to form calcite. Calcite itself is incredibly low solubility compared to the lime, and so about 15 milligrams per litre. And so it's probably a relatively self-sustaining problem. So you go, well, why are you looking into it then if it's not really a problem? Well, why it's become a point of a need to do something on it is because there have been sites that had been stabilised, the soil had been improved with lime or cement, and due to the type of drainage, I'm not going into a lot of detail. I've got a case study on this that I could talk about, but it'll take too long. Essentially, where this is developed is that unsuitable drainage has been then installed into our lime-treated material, so suds-type drainage that actively promotes permeation of surface water into the fill, and then also out and through, and then into a watercourse. You shouldn't do that, by the way, because it's not a good thing to do generally, is to direct water into an earthwork, because it's generally not going to do it any favours in terms of its engineering properties, but also it specifically says don't do that in the SUDS manual, the Syria guide for that. It specifically says do not install infiltration drainage into cement-treated material. So it's not a good idea, but it happens. And this is where you get an increase in one initiative. I suppose it's sustainable. We're promoting sustainable drainage. We want to try and have more natural infiltration of water rather than it going into our water treatment systems. So it's generally a good idea. It's been more widespread and more promoted. But that then leads to more people doing it, and therefore more people doing the wrong thing in a certain set of circumstances. So that's why it's kind of increasing, I suppose, on the radar of the Environment Agency, because they're aware that they've then had these problems on sites where you've had a high pH discharge into a river, and then they are quite attentive about how it gets put correct. So it's come on the agenda of regulatory bodies. We then also became aware of BritPave members being challenged over the use of cement stabilisation, and particularly the challenge that was put forward on a site was that the question was asked, can you prove that it won't be a chromium-6 problem? Will you get chromium-6 leaching into an aquifer or a watercourse? Chromium-6 is cancerous. There's no real specific reason why that would happen, because the cement industry has gone to a lot of effort to introducing processes to put iron oxide into their cement so that when it hydrates, the chromium-3 remains non-oxidized or in a lower oxidation state, so it would not be the cancerous or the bad form of chromium-6. So there's no reason to think why stabilisation would suddenly cause that, but that was the logic, and if there wasn't a strong and robust case to say that wouldn't happen, then you can just be refused the permission to go forward, and indeed that's in those examples that's what happened. So that introduced the need. We need to have a response to this as BritPave as a body. How can we control the narrative to reinsert some sense, I suppose, into this supposed problem? So this is now a bit of the background, a theory of how water would flow through soil. So on the left side here, we've got an example of a very dry material. So if compacted dry of an optimum moisture content, you're going to end up with a clod flow based process where water will flow with quite high permeability around the individual clods of your treated material. Whereas if you have a wet of optimum moisture content material that is well conditioned and then compacted, you're going to have a pathway where the water has to go through the whole mass, and therefore the permeability becomes much less, and the likelihood of anything leaching through that is also less. That we can also link that into some direct leaching studies. So these are studies where they've set up leaching cells and forced water through a treated material to see what would then happen over time. And so in this study, they undertook continuous leaching for up to 90 days or 45 days, depending on the variant. And so some things that we can see, it's quite on the left side here, we've got quite a high dosage of binder, so 6% hydrated lime, which is about 4% quicklime equivalent. And so one thing we can see is on the y-axis there, we've got the concentration of calcium in parts per million, and then the time leached. And we can see a difference between the dry of optimum moisture content